All right, welcome back. Let me turn on my timer here so I can make sure I'm only going to be doing a video that's so long, so it's not going to go for hours. Okay, so this is going to be section 1.2, and pretty much the point of this section is verify. Okay, so I always like when you see this term verify, it's like you should really bring a deep sigh of relief because they're not asking you to solve it. All they're asking you to do is make sure it's the right solution. Okay, so they're going to give us a differential equation and they're going to say, well, this might be a solution. Check it. So you don't have to, I mean, it's not that they're going to be necessarily the easiest problems that you've ever seen, but like there's no, well, is it linear, non-linear? How do I solve this one? Do I have to use this technique or that technique? No, just take the derivatives, plug them in, and see if it works. That's all they want you to do. Okay, so we're not, I always see this when I teach this class, like I'll say verify, like on their first quiz, I'll have to go verify. And the students will go and they'll tie themselves in a knot trying to solve it. Like I didn't want you to solve it. I just wanted you to check it. That's it. That's all you have to do. So let's say we're given a differential equation. Let's say we're given 4x squared. See, I picked this one on purpose because you're going to learn the how to solve this one for quite some time. Okay. So we'll solve that. Okay. And we'll say has a solution. Okay, and what solution do we have here? We have y is equal to 2x to the 1/2 minus x to the 1/2 natural log x. Okay, so, and verify y is a solution. All right, so we don't have to figure out how to solve this. That's not part of it. Okay, all we have to do is take, well, what's y? Right, y is equal to 2x to the 1/2 minus x to the 1/2 times natural log x. Okay, and then we need two derivatives, right? We need to plug in a y double prime here. So y prime, right, is equal to the 1/2 comes down in front, so we just get an x to the negative 1/2. Nice, kind and gentle way of starting. And then what did I do here with this? We said minus, and then hey, I've got a product, right? We got to use product rule here. So derivative of the first, right, times the second, plus the first, x to the 1/2, times the derivative of the second, right? So we just get x to the negative 1/2 minus 1/2, x to the negative 1/2, natural log x, derivative, right? Minus carries through, so minus, we have x to the 1/2 over x, so that's x to the negative 1/2. Hey, what do you know? That's, we have a positive x to the negative 1/2 and a minus x to the negative 1/2. That's convenient, right? It's almost like this problem came out of a textbook somewhere. X to the negative 1/2, natural log x, right? And that's my y prime. Like, well, I don't have a y prime. I need a y double prime. So we're not done yet. All right. So now we have to go ahead and take another derivative. So we have, again, right, derivative of the first. So that's going to be 1/4, right? 1/4 x to the what? Negative 3/2, because we take that times the natural log of x plus, right? No sign changes here. Derivative of the first, well, derivative of the second, right? The first times the derivative of the second, that's 1 over x. So here we have, this is, let's clean this up a little bit. Negative 1/4 x to the negative 3/2 natural log x minus 1/2. And it looks like we have x to the negative 3/2. So that's my y double prime. Now we get to verify this, right? We go back up to the beginning. We say, okay, there was a 4x squared y double prime. What do we have here? Plus y, and let's check to see if it's equal to 0. So we have 4x squared y double prime This was 1/4 x to the negative 3/2, natural log x, minus 1/2 x to the negative 3/2, right? Plus whatever y was. Y was that first thing they gave us. That was going to be 2x to the 1/2 minus x to the 1/2 natural log x. That's from this point, right? That was a given. Okay, and does it, does this come out to be 0? Well, if I plug this in, right, we get the 4's cancel, so we're just going to have x, and this is 2 and negative 3/2, so that's going to be x to the 1/2 natural log x, okay, minus, looks like 2x to the 1/2. And then what are we going to do here? We're going to add this to 2x to the 1/2, because that's going to come down. And we're going to subtract off x to the 1/2 natural log x. And indeed, right, all of this stuff cancels. It's all very nice, right? We can see this. Now, you have to remember that sometimes books lie to you and they say verify it's a solution, and it is absolutely not. So don't be like, well, I didn't get that it was a solution, I must be wrong. Like, that's not true. Sometimes they say verify, and the whole reason they're asking you to verify is because they lied to you at the beginning and gave you a solution that wasn't. Okay, so just because you're not getting this thing to turn out to be the same thing does not mean that you're wrong. It means that it may mean that they lied to you. It might mean that you're wrong, but double check that before you go in and condemn yourself and say, wow, I didn't get this. All right, so that's verify, and we'll do a couple more of these, but like I said, I was always very relieved when I saw this question on an exam, because I didn't have to think about like, what technique should I use in order to solve this? Oh, one thing that we do have to recommend though is that would be true, right? X would be greater than 0. The interval in which your solution applies is very important. So I think in the original problem, they actually specified x was greater than 0. So x is greater than 0, because you plug in 0 for natural log, that's not going to work out so well. You have a fraction, right? Zeros, and this is not going to work out so well. So it's really important to remember that when we are taking derivatives, we're solving for equations, that the interval that our solution is good on is usually a continuous function. The x, the value y is continuous on that interval, and it exists on that interval. Because if you get like stuff where it doesn't exist, or it's like you get a y prime that's undefined because you got something, you got a function that has like a vertical part in it, it's possible, like, you're typically only going to get one solution to these things, right? Or one family of solutions. But if you end up trying to take derivatives over places you can't take derivatives, it's possible like this diverges and you get like 2 different solutions. We'll talk about that a little bit later, but that's certainly a concern. So make sure, and I usually will go with the no nonsense rule of, when we have a solution, we're going to talk about like where that solution exists, and like, well, what if x was negative? Like, well, then this problem couldn't have started, right, if x was going to be negative, because there's no way this could have been a solution to begin with. Okay, so I had a linear algebra teacher that would just, for those of you who are in linear algebra, there's going to be a lot of times where it's like, can I multiply these 2 things together? Like, no, you can't multiply them. Like, we're not talking about that case. We're only talking about the cases where like the answers actually exist. Okay, but it is something that we're going to revisit in a little bit. Okay. Let's see. The next thing they'll talk about is they'll say we have n parameter families, n parameter solutions. And what I mean by that is like a 1 parameter solution, i.e. you have a C. Okay. If you took 2 derivatives, right, you're going to have a C1 and a C2. So you could have a 2 parameter solution if you have a 2 parameter solution. You might have a C1 and a C2. three parameters, C1, C2, and C3, and so forth. Most of the time we're dealing with those because most of the applications at worst are going to be second order differential equations. So most of the time we're dealing with this case here, maybe this case. But mostly it's going to be a system of equations that we're going to have to solve. And again, for those of you who are in linear algebra, like, wow, enjoy this. Because if you get fourth order differential equation and you've got a 3-parameter solution or a 4-parameter solution, you're going to have 4 equations, 4 knowns, and you've already done a hard calculus problem. Doing a hard linear algebra problem on top of that doesn't really seem to be fair. We get to the computer stuff, it might be a little different, but that's what we're dealing with. So this is y, say, equals 1 over 1 plus c e to the negative x. This is a 1-parameter, right? This is an x. This is a 1-parameter solution, okay? And they're going to claim that this is the solution to, let's see, this is y prime is equal to, I think this is y minus y squared, okay? Now, they said we want you to solve for this. We're going to have a y of 0 is equal to negative 1/5, right? That's when x equals 0, y is equal to negative 1/5. They didn't ask me to verify it. I don't need to go through and take a bunch of derivatives and square this thing and then see if it actually works, right? Well, I only need one derivative. But they didn't ask me to do that, right? This looks delightful. We'd have to bring this to the numerator, do a chain rule. No. Square it. It all looks too much fun. But they didn't ask us to verify it. All they said is find the parameter, find y, find the c, okay? Your constant of integration, find c. So all we have to do is plug in 0 for x, right? We're just going to say, well, this is 1 over 1 plus c times e to the 0. You know that that's 1 is equal to a negative 1/5, okay? So we have 1 over 1 plus c is equal to negative 1/5. All I'm going to do is invoke reciprocal rule. So we have 1 plus c is equal to negative 5. Subtract 1 from 5, we get c is equal to negative 6, and we're done. If you wanted to cross multiply that instead, you go right ahead and do that. Once we get to here, there's like 8 ways from Sunday to solve it. Pick your favorite one, okay? So that's all they're asking us to do for stuff like that when they say find the parameter. If they happen to give us a y, and they usually will, they are not asking you to solve a bunch of stuff. Okay. Now, sometimes it gets a little bit more difficult. Okay, we have, say, y is equal to c1 e to the x plus c2 e to the negative x. It's a 2-parameter solution, right? Because we have a c1 and a c2, and they say this was the solution to y double prime minus y was equal to 0. Okay, and they give us a couple of boundary conditions. These are often called initial value problems. So you see the IVP, that's initial value problems. Sometimes they'll call them boundary value problems. BVP. Okay. Usually with BVP's boundary value problems, they're usually like 2 different regions that they give you the boundary on. Like they'll be like y of 0 is equal, and they'll say y of 10 is equal. Okay, so that's typically how boundary problems work. But initial value, right, because both y of 0, y prime is 0. They also have to give us some stuff, right? They're going to tell us that y of 0 is equal to 1. So this is still given, right? We're still talking about the problem setup. This is what you're going to read out of the textbook, okay? And then y prime of 0 is equal to 4. So this would be an initial value problem, initial being when x is equal to 0. Okay, it's still a boundary value problem, but because they're both zeros, they say initial value. These are not terminology that you're really going to have to deal with. Okay, I'm not going to ever ask you, like, distinguish between these two. No, not asking. I'll ask you to solve it or do this, but I'm not going to ask you what the differences are. Okay, so we probably need to figure out what y prime is because we have a value for y prime. We don't have to verify it. Okay, they're just asking us to say, well, what's y and what's y prime? So let's see here. We have y prime is going to be, right, c1 e to the x, and then the next one is going to be minus c2 e to the negative x. We took a derivative, right? So the negative 1, right, the chain rule, we have e to the negative x is e to the negative x times negative 1. There's your negative 1. Okay, so we have y is equal to c1 e to the x plus c2 e to the negative x. We have y prime is equal to c1 e to the x minus c2 e to the negative x. And all they're asking us to do is like, well, plug these things in. Okay, so if I plug in 0, right, all of these terms, right, when x is 0, all of the e to the whatevers, they all turn into 1. So I have c1 plus c2 is equal to 1. And I have c1 minus c2 is equal to 4. Okay, they're not all going to be this easy, all right? But again, we have two equations, two unknowns. How many ways do you have to solve this? Okay, if you're linear algebra, you're going to learn about 8 more ways to solve this. So C1 and C2, we have two C2, or two C1s rather. C2's cancel, and that's equal to 5. C2, C1 rather. Why do I keep calling C2? C1 is equal to 5 halves. Plug this back into whatever equation you'd like. So we have 5 halves plus C2 is equal to 1. Subtract on both sides, subtract on both sides. So we have C2 is equal to 2 minus 5 is minus 3 halves. Okay, so our actual function that's going to satisfy every condition that we have here is going to be 5 halves e to the x minus 3 halves e to the minus x, and that's what they wanted us to find. Okay, so again, don't read too much into what they're asking us to do, especially in chapter 1. Okay, I promise it gets harder, but at least at the beginning here, we only have this little bit. However, speaking of harder, okay, this is like nitpicky harder. It's not necessarily harder. So we'll have a 3x squared minus y squared is equal to c. Okay, and they want to verify this is the solution to y times y prime is equal to 3x. So a nice, right, nonlinear first order equation because we have y times y prime, so that's an interaction between y's. It's not linear anymore. Okay, but it is ordinary because even though we have an x and a y, we're just going to take the derivative with respect to x. So first order, nonlinear, ODE. Okay, so take derivatives of both sides, right? So we have to use implicit differentiation here, don't we? So we have a 6x minus, we have 2y, and then there's a chain rule. That's the implicit differentiation. Y prime, derivative of a constant, 0. Okay, so what we're going to have here is 2y times y prime is equal to 6x. Divide both sides by 2. We have y times y prime is equal to 3x. That's exactly what we wanted to show. So yes, this is a solution to this differential equation. Yeah, pretty nice. And then they go nuts. Okay, then the book goes nuts and asks you a whole bunch of follow-up questions about this. I'm like, what am I supposed to do? So what they say is, we have a boundary condition. So they really want, instead of C, they're going to specify a specific value, and they're going to say 3. Okay, so they want us to graph this and like kind of explore the solution space to this differential equation here. So the first thing they're going to say is graph it. Like, really? Like, oh, we could do this, right? This is divide both sides by 3. We have x squared minus y squared over 3 is equal to 1. And if memory serves, this is a hyperbola, right? By the way, differential equations. This is the first class you probably have where everything that you ever learned in your math career will somehow become relevant. And when you've forgotten it, you're like, how did I forget this? Like, that's the way it is. If you're going to go on to math, if you're a math major, you're going to go take other classes, and all of a sudden, like, even the stuff that was like, I don't remember learning that in like ninth grade geometry, but I guess I did, and now I have to remember it for some reason. Okay, but this is the first class of that nature. So hyperbola, it's transverse axis or the x sides, right? So we set y equal to 0, we get x is equal to positive or negative 1. We set y equal to 0 or x equal to 0 and change the negative sign, right? We're going to get square root of 3 here. We're going to get a negative square root of 3. And of course, you remember, right, how to graph a hyperbola. You make the little box, right, using the method of intercepts here. Here's my vertex. Here's my vertex. We have, which color should we make? We'll make our color that color, like our asymptotes, right? We have our little asymptote that goes through the piece here. Pretend these are straight, okay? And going back to my graph. Okay, so we've got a hyperbola that looks something like this, right? Because it's got to hug its asymptotes here from the vertex. All right, and there's our function. There's our total solution here. All right, but don't answer yet, because this is not a function, right? If I said what's y, okay, and here's a weird sort of notation. When you have a y equals, right, that's like your solved solution. They'll say that the phi is your actual solution. These will often be the same, but yeah, it's just a small notation thing where it's like, now we're certain it's a solution versus we just, please use y. Don't make everything phis. Okay. But the book will say, well, phi1 is equal to, no, they want us to solve. They want us to solve explicitly for y. I won't always ask you to do this. If it's too difficult, I will often just say, leave your solution implicitly, or not written explicitly as a function of y, right? You could leave it like this, and I'd be really happy with that. Unless we say solve explicitly for y. In this case, we're going to say, well, we have 3x squared minus y squared is equal to 3. These guys will swap, so we'll have y squared is equal to 3x squared minus 3, which is y squared is equal to 3 x squared minus 1. So y is equal to plus or minus square root of 3 times the square root of x squared minus 1. Could you have said x squared minus, or the square root of this thing right here? Absolutely. But remember that when we talked about, where can we take a derivative, your function has to be continuous, okay? And it has to be a function. So right now, right, hyperbolas are not functions because they fail the vertical line test. So what we have to do is we have to break this down into stuff in quadrant 1, right? So y is equal to square root of 3, square root x squared minus 1, right? For x greater than or equal to 1, right? Because we don't want to take a derivative in here. If the function doesn't exist, you're not going to find a derivative in here. So we're specifying our region. We have quadrant 2, which is y is equal to square root of 3, right? It's still positive. It's still above the axis. X squared minus 1, and it's for x is less than or equal to negative 1. Delightful. Quadrant 3, okay, y is equal to negative square root of 3, x squared minus 1, x is less than or equal to negative 1. Or quadrant 4, y is equal to negative square root of 3, square root x squared minus 1, x is greater than or equal to 1. Okay, so those are your 4 possible solutions. So, right, you really have something that looks more like this, right? We've got You've got a solution over here, right? That's one possibility. You've got a solution over here. That's another possibility. We wanted to make sure that we could take derivatives, so we'll go ahead and do over here. That's a third possibility. And then we have something over here for a fourth possibility. And if they hand you if they hand you an initial value, where is that initial value? Is that initial value in quadrant 1 or boundary value? Quadrant 1, quadrant 2, quadrant 3, or quadrant 4. And that's how you pick your actual solution. Okay, I typically don't quite get that nitpicky over what your solution is. I'm just happy you could solve the things. We could do the geometry a little bit later and try to figure out what's going on there. But that should give you enough to kind of unroute, like, why did they do that in the homework? This is why they did that in the homework. Okay, it was because they wanted a nice continuous region that was a function, so no vertical line test stuff. But that's everything that they're going to. Okay, most of the time we don't quite get into this much detail about solutions. Okay, but if you're looking at the WebAssign stuff and you're like, why did they? This is why. Or if you're looking at a book and you see the answer in the back and they're like, they've got this whole thing listed out, this is why. Okay, so I'm going to go ahead and leave us with that, and I probably want to post tomorrow about 1.3 and chapter 2. Okay, so let's stop there.